So to calculate sample sizes, we need to be concerned about the confidence interval we want. Recall that the confidence interval is determined by how precisely we hope that our estimate captures the population value and how confident we are that indeed the range captures the population value. The equation, this equation is for a confidence interval about a mean. So Ci, the confidence interval, is x bar, which is our sample estimate, mean, plus or minus z times the standard error of the mean, s over the square root of n. Now, you should see these two components in there. The precision is the plus or minus component, so the value of z times s over the square root of n determines the range of our confidence interval. And s over square root of n is an indication of the variance in the population, which is what affects our certainty. There are similar equations for estimating confidence interval for proportions, and we'll look at those later. So sample size determinants then are these three. The precision desired, how large is the range of values around the sample estimate. So if we're talking about a mean, we're estimating the mean plus or minus some component. That's our precision. The certainty desired is how confident we are that the population mean is indeed in that range. And the population variance is how much values are dispersed in the population. Those three things determine sample size. As we want to be more precise, we'll need a larger sample. As we want to be more certain, we'll need a larger sample. As the population variance increases, we'll need a larger sample. These are the sample size equations for proportions, estimating proportions and estimating means. Now, all of the equations are given to you in a separate sheet, so you'll see these and have these available to you as needed. For proportions, sample size, n, is equal to z squared pq, the quantity divided by e squared, where e is the tolerable error expressed as a percentage. So the sample size depends on z, which is a measure of the precision that we're tolerated. Remember, z is a measure of how many units out from the mean a given proportion of values fall. PQ is a measure of the variance for populations, where P is the proportion that you're trying to estimate, and Q is 1 minus P. And E is the proportion of error you're willing to tolerate. So let's say that P is, let's say you were trying to estimate the proportion of people who have tried a given brand, and P, in fact, was 20%. And you wanted to, the certainty that you were interested in was you were willing to tolerate an error of 2%. You wanted your estimate to the range, your confidence interval, to capture the population error within plus or minus 2%. Well, what certainty do you use normally? Well, the standard certainty is 90 or 95%. So most academic researchers use a certainty of 95%, which corresponds to an alpha of 0.05%, where alpha is 1 minus the confidence level. In a lot of applied research, researchers are willing to tolerate more uncertainty, so they'll use an alpha of 10% with a corresponding confidence level of 90%. And that determines the z. So you have a z-score for each alpha level or each confidence level. And so you can see where the confidence comes in terms of the z. Again, the PQ captures the population variance, and that E of 2% is our decision about how precise we want to be. So each of the three components comes into play in estimating sample size. And we'll go through some problems that illustrate these calculations momentarily. Similarly, the sample size equation for estimates of the mean is n equals zs divided by E, that entire quantity squared, where E is the tolerable difference error in whatever measure the scale uses. So it could be dollars, it could be years, it could be points on a 7-point scale or a 10-point scale. So again, you see Z, which is an indication of how far away from the mean we're willing to range for how certain we want, or how precise we want to be. That's our confidence interval. S is the standard error or standard deviation of the population, which is a good indication of the variance in the S is the standard deviation in the sample, which is an unbiased estimator of the variance in the population. And E is the error that we're willing to tolerate. So Z captures our precision, S captures the population variance, and let me back up. Z captures our certainty demands, S captures the population variance, and E captures the precision. So again, all three components in this expression for sample size calculation. So we have these clear and simple mathematical equations for calculating sample size, but in fact, most research doesn't use those equations because there are significant challenges to calculating sample size. The first one is that the population variance is very difficult to estimate. And you'll notice in both those equations we had either a direct estimate of population variance, or we needed the sample variance as an unbiased estimate of population variance. And of course, how do you get a sample variance in order to calculate the size of the sample that you need to draw? So if you don't have a sample, how do you know what the sample's variance is going to be? A second challenge is that almost all research has multiple variables, and those variables will have different variances in the population. So if you want to have a certain level of precision and confidence for all the variables, then you need to make sure that the sample is large enough to handle the one measure that has the most variance in the population. And sometimes there'll be one or there'll be some group of variables that are so varied in the population that it's just not feasible to make the population big enough for those. And finally, these questions about certainty and precision need to be made by the researcher in conjunction with management. And managers rarely understand this well enough or can apply it well enough to their management problems to know what level of precision and certainty to rely on. And as a result, we often use the sort of traditional confidence levels like 95% or 90% and fairly traditional precision estimates like plus or minus $100 or plus or minus 2 years or plus or minus 0.2 of a scale point without any very strong reason for why those are appropriate in a given situation. So because the difficulties of getting good estimates of population variance, either time or expense, applied research typically uses guidelines. And those guidelines are that larger samples are needed when the decision is very important. So when the decision is important because lots of money is at stake, for example. Usually those decisions require higher confidence. Or if the population variance is expected to be high, and of course we know that if population variance is high, there'll be more error in our sample, and so the sample will need to be larger to offset that. Or if we know that we're going to subdivide the sample to look at a number of different categories, or categories with a number of different levels. Or if it's simply inexpensive, the costs of increasing the sample size are low, then go ahead and make a larger sample. Or even if they're expensive, but we have a lot of money, so we have plenty of resources to recruit and take advantage of a larger sample. So when any of those conditions apply, it makes sense to go for a larger sample size. And I'll try to be more specific about what large and small samples are as we look at specific statistical tests and specific research questions. And naturally, the opposite conditions indicate that smaller samples are adequate when decisions are unimportant, when rough estimates are sufficient. We don't need to be very precise or confident about our estimates. When we think the population variance is low, when we're not going to divide it into very many subsamples, or when it's very expensive to increase sample size, or we simply don't have much money to increase sample size.